Okay, so welcome to lecture. Welcome to lecture 5 on NLP with deep learning. So today we actually need to finish a little bit from the last time and something we discussed yesterday in the exercises as well. So it won't be new now, because now you have a little bit of practical experience as well. So what we're gonna tackle first is to finish basically deep learning. So we're gonna finish deep learning today in the beginning of the lecture, and then deep learning, and then we can move on to NLP. But it's actually true. And then we actually will talking about the language modeling part of NLP. So it will be really, the first part is more like generic for deep learning, and the second part will be really about language and how to model language. It's not about text classification, it will be about a little bit of text generation as well, or understanding the flow of language. So that's why we call this here text generation 1. So the first lecture on text generation, because we might be generating language today actually. But let's finish first. Okay, so last time we discussed the linear models, and that linear models they can tackle only problems which are linearly separable. And now this should make much more sense after the yesterday exercise. I mean, now you see what's going on here. Okay, wow, you actually built this thing already. I mean, not in this nice user interface, but you know what's going on. So we have here the input features, which is the x vector. So these are these two nodes. We call them input nodes, whatever. And here we have the output, which is, I guess here in this example, it's not explicit, but it's I guess it's a sort of sigmoid over linear layer. Okay, so we have the linear layer. So here's the output of the sigmoid, and it's doing classification task, and we have this nicely separable thing, and it's learning that the hyperplane here separating those two classes is this sort of linear function in between. Okay, so it can really classify this problem with almost 100%. Well, there's training loss 0, so it really learned everything pretty well. So everybody now understands what we're showing here, like very in detail. Like we have features and we have the model here. Should be clear now after you finish the exercise yesterday, okay? And that's fine, but unfortunately in reality, our data points are not mostly are not linearly separable. So we have this issue like this OR function, where we have in 2 quadrants, we have one class, the blue dots, and in the others, we have the red ones. And if we use the same model, so again, these are 2 feature vectors, their position on this coordinates, and here again linear function with some sigmoid on top of that, we cannot really draw a line here. I mean, we can draw a line. I mean, the model learned something. The model, while minimizing the loss, it tried to fit it somehow here in between to have like the least error as possible. But it's not really solving a task. It's making a lot of errors, obviously, because it's not solvable by a line. Okay, makes sense, right? So what can we do? We need something more powerful. And this is something like you definitely learn in machine learning 1, all the kernel, SVMs, kernels, and stuff like that. Maybe, I don't know. Maybe you will learn later, but. So deep learning comes with another sort of approach how to solve this non-linearly solvable tasks. And this is by stacking layers on top of each other, okay? So what if let's look here. So we have this input feature, and here's our output layer. What if we just stack something in between, maybe another linear layer, so everything will be connected like that, and then everything will be like that, basically. So what will happen? We stack another. So what is the linear layer doing? What is a linear function? We have input, and we're multiplied by the matrix and some bias, but whatever, we're doing what again? What is the linear function doing with my data point? It takes a data point somewhere, and it's doing something, a linear transformation. What is that? Anyone remembers that? So linear function is doing something with our input. When we multiply a vector by a matrix, we're doing a thing. Any idea? You take a vector or a point, which is a vector, you multiply by a matrix. So you're doing some linear operation on this point. Basically, you're doing what? You're You're projecting the point to some other space, right? It's a projection. You take a point, multiply by a matrix, and then depending on the dimensionality of the matrix, you might be projecting to a space with another dimensionality, right? So we had this example like phone projecting from 3D to 2D. You take a vectors, multiply by a matrix, and project on some low-dimensional space, maybe. So it's a linear operation, okay? And lines will be lines after this operation. This is important. So this is why you can't solve it by just linear function. Okay, so what if you take another projection after this projection? So you project in one space, and maybe then there will be another projection to another space to do it somehow more tricky. So what will happen? Maybe it's a good idea to start with. So how can we do that? So again, here's the first sort of simple model we had, the first linear projection. So we have the input features and weights and biases for this projection. So this is projecting to space of dimensionality. Okay, let's make it clear. So this is the input dimensionality of the X. Then the matching dimensionalities of the weights and bias. So this output will be in D1. Okay, because we're projecting from the input to D1. Okay, cool. So then we need another projection from D1 to D out. And how we do it is basically, again, multiplying this output. So here, this is the first function here. And then we multiply this output by another matrix plus bias, which we call W2 and B2, because it's like a second layer in a row. And of course, we have to match the dimensionalities again of the matrices, right? So you know how to multiply a vector by matrix, so it has to match. And we get an output in dimensionality of D out, which could be a scalar. If you do like a binary classification, you have a scalar and do the sigmoid on top of that for classification. Or what was it last time? Okay, softmax. Who remembers softmax? What is softmax doing? I said you should remember. So who doesn't remember yet? Learn it. What is softmax doing? You had an idea. You were raising your head. Okay, so maybe give it another thought, okay? So anyone else, what softmax is doing? What is softmax doing?
So it transforms a general vector to a vector that sums to 1.
Okay. So it takes a vector of any values and transforms into a probability distribution, basically, because all the values after the softmax transformation will sum up to 1 and will be between 0 and 1. So this is what softmax is doing, right? And we use softmax we use sigmoid for what? For one type of classification. Which type of classification? What is? Sigmoid is the last thing before you do classification into how many categories? Into 2. It's a binary. So sigmoid is like binary classification. In contrast, softmax you use for n classes, because you basically create a probability distribution for each, probability of each class. Okay, cool. So this will be and depending on our problem, this output will be either one real number for sigmoid or multiple vector of real numbers, and then we put softmax on top of that. Okay, so this is nice. So we have 2 linear transformations after each other. So what do you think? Will it solve our problem? Will it solve this issue? We're stacked 2 linear transformation after each other. So we make a linear projection to one space, and then we make a linear projection to another space. Can these projections solve this issue? Who thinks it will solve the problem? Raise your hand. Okay, 1. Who thinks it doesn't solve the problem? Multiple. And the other people are still thinking this is fine, this is okay. So why won't it solve the problem? Why do you think it won't solve the problem?
Well, we still have the linear output. So it stays linear, and I don't think that we can divide this kind of thing with just a linear function. Exactly. It will stay linear. If you stack linear functions after each other, it will still be a linear function. I mean, you can here take the formula and multiply the stuff in between here, and you will get a linear projection. You will get a linear function of the inputs.
right? So it won't move a needle. It's just extra complexity in here, in the middle, like we're adding something in here, but it will stay linear. Linear operation after, after each other will be linear operation on the input. Okay, this is important to know. So it doesn't solve the problem. So can we solve the problem? Can we do something here with this computational graph? Oh, by the way, this is again a computational graph again. So we're using, so this is a linear node, this is the input node, and this is again a linear node. So you are now getting very familiar with the concept of computational graph and the function of these nodes in there. Okay. So what can we do to break the linearity? Can we break somewhere the linearity here? Can we introduce some sort of nonlinearity in there to solve the problem? And if so, where could we put it? So I have one idea. So if we put, after here we have a sigmoid or softmax. So this is already nonlinear. This is fine, but it's not solving the problem. It's just turning this into probabilities, but not really wrapping the space. You have an idea? After that?
These neurons with sigmoids.
So here, would you put it somewhere here or after, or?
Like the ones that already got added in.
Here? With sigmoid.
That's after the same thing again.
Okay. Yeah, you're on your way. Exactly. So what we're gonna do is we introduce, so you would basically put it here, somewhere here. You would introduce, in between those two linear transformation, you would introduce some sort of nonlinearity. So the projection will, in the first projection, will not be linear anymore. It will be somehow wrapped or warped. Some nonlinearity will occur. So we'll project in a space, and the space will be somehow distorted. So lines will not be lines anymore. And this is what we want. And this is exactly what we're gonna do. So we're adding here in the middle. So this one, yeah, as I said, like if you keep it like that, here we added 4, again 4. you see the computational graph from yesterday is exactly the same thing we were doing. We have 4 linear nodes, so we call them neurons here, obviously. We have 4 neural nodes, and each of them is fully connected. So this is a layer. You see it, we call it a hidden layer. This is a layer, this is the input layer, and we fully connected everything with everything. Okay, so this is what we built yesterday. But now still we have a linear function here, which is also called activation function on the layer. So this is still linear node. So there's nothing nonlinearity. So it won't do anything. It's still unsolvable. So we introduce here, as you suggested here, after the output. So this is the output of the hidden layer, so-called hidden layer, because we don't see this output. We don't control this output in a way, like explicitly, because the output of that one will be controlled by the loss and the gold label. So we observe this output, but here we don't actually care. It's somewhere in the middle. So in the hidden layer, and we're adding some sort of nonlinear function. Okay, so we want to break linearity, and we're adding nonlinear function, which is basically applied to each element. So each sort of node or each neuron, here we're adding some nonlinearity on each of the node, or after each value of this node. So we're adding some nonlinearity. Do you have any idea what kind of nonlinearity can we use? So what is nonlinear function? Well, it's a function which is not linear, and linear has a definition, but what could we already had some nonlinear functions actually. We know nonlinear functions. So what is doing nonlinear function? It's producing something different from a line. So for example, sigmoid is a nonlinear function. Yes. So for example, sigmoid is a nonlinear function. And actually, sigmoid had been used in deep neural networks for decades, maybe here as a nonlinear function. But there's better ways, or much faster, or empirically better nonlinear functions, and which are basically the go-to function nowadays in NLP. And these are, okay, so let me think. If you take a line and want to make it not a line, what is the simplest thing you can do? So you have a line and you want to make it not a line. What can you do with that? Yeah. Yeah, wait, you can square it. Okay, that's super easy. Maybe there's something much easier.
Oh, there was an equation function that's just all values lower than 0, it's 0, and
yeah, okay.
it gets, like...
This is the answer. I mean, the first answer, I would say you just break it. Basically, you take a function and you just break it somehow, and it's nonlinear, right? It will be partly linear, but not as a whole. And exactly that's what you're saying. This is one very popular. It's called rectified linear unit activation function, which is a very fancy name, ReLU. So you should know ReLU, absolutely. What is it doing? Well, okay, so for all values, non-negative values, it remains the same. So it's basically identity. So it's the line here. For z greater and or equal of 0, it's the input. And the rest is just zeroed out. Is it a nonlinear function? Yeah, absolutely, it's a nonlinear function. Why would we do that? Okay, so there is one trick. It's not a trick. There is something which makes this function very easy. So remember, this function, this g, will be part of our computational graph. So what we need, and we know how to compute it. So we have this value now. What else do we need to compute for each node in our computational graph? We need two things: the value and something else. So what? What was that? Oh, okay. No. Yeah. Awesome. Love it. Zoom is amazing. What else? Okay.
I think it's the MacBook.
It's the MacBook.
And the new update has something you can also do thumbs up. It doesn't work always.
No.
I watched it on YouTube. Yeah.
Okay. Awesome. Awesome. I love it. It's gonna make. Okay. I'm gonna do it at the end of the lecture. You know, like. So. But okay. Coming back. So what is two things we need for each node to be implemented? Like you implemented already like 1,000 times. Well, maybe 4 times in the exercises. So each node has to know its value and the local derivative, the derivative of the function. So what is the derivative of this function? What is the derivative of this function? Yeah, you said it. It's 1. It's 1 for all values. So d ReLU d like that dx is 1 for x, right? I mean, this is a linear function and it says derivative 1. Yeah.
Couldn't there be a problem when we have as input a linear function which has like +7 at the end, some kind of x, and then we just say that if we
so if +7 is coming here as the input, it will be +7 as the output. That's fine. So everything is still the same. Okay, but back to the derivative. And what is the derivative for this function? What is the derivative of a constant function?
Nothing. 0.
Well, no, nothing. Nothing is a 0. Yeah, exactly. Oh, that's actually pretty nice. Oh, because this is like super. You know, it can't be any simpler. The partial derivative is this 1. So you don't even if you're then multiplying in the chain rule in the computational graph, you just multiply by 1. So it doesn't blow the gradient or doesn't make it very small. It keeps the gradient the same. Remember, we are talking about like exploding gradient. Like the gradient is very, very, very large, like almost infinity. Some functions can have like this very large gradient. This function has a gradient of 1, always constant. And then the 0. Okay, so maybe some errors propagated due to backpropagation will be ignored, will be zeroed out. So it's also interesting property. Okay, so this is a nice function which is empirically really, really powerful. But there are others, like a sigmoid. There's also 10h, like tangents hyperbolicus, which is almost like a sigmoid, but it's shifted as far as I remember. But you might want to correct me. So this is, I guess this is 10h from, and it might be from -1 to 1 or minus half to plus half. I don't remember exactly, but sort of this function. It looks like sigmoid. It had been used in deep learning as well. But ReLU is basically a go-to function for nonlinearities as well. For these properties, it's super easy to compute gradients, no underflow or overflow of the gradient. Okay? Any questions? Well, I have one. What is the gradient here? Well, okay, no, we have the answer here, but yeah. What? Well, you have to make arbitrary decision, basically. I mean, the gradient. So if you really look at this, like what is a gradient on this edge? I mean, this is like not continuous function here. It's basically broken. So you have to make arbitrary decision. Rarely in the praxis you will get exactly value of 0. So and you make a arbitrary choice. So say like if it's 0, the gradient will be 1. Okay. So this is like a corner case which you just take care of, and it doesn't come at all in the praxis. I think there is a name for it. It's like a not continuously differentiable, something like that. Yeah. So the tangents H is continuously differentiable everywhere. This not, but you make a choice. You have a question?
Yes, my question from before, but now I can phrase it better. The problem is that we just map it to 0. So if our input is like something +7,
yes,
in the case that that is smaller than 0,
yeah,
we wouldn't add the 7, but at the point of like 0, we would add the 7 if we just put that through.
yeah.
So we would have a break in our function. Is that okay?
Yeah. Okay. This is so. There is a reason why there is this. Okay. There's maybe a little bit deeper technical or philosophical reason why there's a zero output of this function. Because what you want to model sometimes is that not all these neurons, so now neurons like the nodes, so-called fire. So it comes from really the analogy of a brain where you have neurons and axons, and sometimes the neurons are activated through the other neurons, and then where they reach some threshold, they were fire, so to say, so activate others, so send the signal farther on. But sometimes you just don't do send anything. It just zeroed out. If they don't get enough input, they don't fire. They keep calm, so to say, and there's no output. And most of the time, actually, not all the neurons should be activated. Just maybe very few of them. Responding to the input, there is some path in the neural network which needs to be activated, and the rest is just inactive for this task. And this is modeled by this ReLU in a way, because it says, yeah, okay, you can ignore if this is like if the value is the input value, which is before that is the sum is a linear node. So you sum up all the inputs, make the linear activation, and you get some real value output. And if the real value output is negative, then you just don't care. There is no gradient, no error. You just ignore the output. If this is positive, then you go on. So this is the analogy sort of and the inspiration from sort of the sparsity of these neural networks. At least this is how I understand it. I mean, I never really studied the deep theory of deep learning, but that's what I remember people saying at the ReLUs. Okay, any other question? Cool, so let's move on. So we have ReLU. Now we edit here, so we extended our playground here. Oh, by the way, this is real playground. I mean, I really suggest you to go there and play around with this stuff, because it's really nice, because you see how the loss is minimizing and how the function is learning. You can add neurons interactively, and it's really fun. It's really nice playground. So we have this activation ReLU here now, which we edit to each of those neurons of the hidden layer. And it's squeezing the space somehow that at the end of the day, after this projection and the nonlinearity, before the final linear function, it will be sort of not linear anymore. And here we see that this function is actually being able to learn these so-called exclusive OR function. Okay, so exclusive OR means either or, but not both. Okay. So I have any questions? You were no. Okay. So this is cool. I mean, now we implemented basically, we implemented something which is deep learning already. I mean, this is like one hidden layer neural network, and there are like billions properties of these things, like theoretical ones. Actually, if you have enough hidden so-called neurons, or these nodes in the one hidden layer, you can approximate any function. So I think there's a theory saying, like theoretical proof saying, given large enough size of the hidden layer, just one hidden layer and some nonlinearity, you can approximate any function, right? In praxis, you don't want to go wide, you want to go deep. So maybe stacking more layers after each other. And that's why it's called deep learning, okay? Why is it called deep learning? Because we're going deeper in the network. So play around with this thing and if you add more hidden layers, you will see how it learns different sort of shapes of functions. And here you can choose also much more complicated data sets, like this one, where there's like 2 spirals of data set in one each other, which is kind of complicated function to learn in the first place. So you need to add maybe more hidden layers or maybe more hidden neurons. I really suggest, you know, you go and play with that, because it's really fun to see how really the space is nonlinear, but the function is able to learn it with enough hidden layers. Okay, so hidden layers, one or more hidden layers, we call it deep learning. So now you learn deep learning. There is no more magic around it. Well, it is, of course, there's like lots of magic around it, but this is the basic principle. Okay, so we're adding layers. Of course, you can add more layers. Yeah, it will learn some other functions, right? And you can make it fully connected, and more and more and more. And this is basically the new question: how many layers and stuff like that. It's more like empirical question. So there is no like good answer. It depends on the task, depend on the complexity of the on how many data points you have and stuff like that. Okay, but typically we have deep functions here, like nested functions. All right. So I have a question. Where do you have an example where this could happen in NLP? Like, do we really have an NLP function? Sorry, NLP task where this exclusive OR might take place?
Negation and language. Yeah, single mode, double mode, and maybe
Negation, yeah, okay. Negation is a good example. Yeah, okay. So I'll try to come up with one example which is very stupid, simple, but maybe shows the thing. So we have a vocabulary now of 3 words. Okay, so vocabulary is now 3 words, which means our feature space has 3 dimensions. So our words are not, bad, and good. Is it realistic? Could be. You can build this stuff. Why not? I mean, you can have vocabulary with 3 words. Then, so these are like 3 dimensions, and so these dimensions for presence or absence of the word in the sentence. So sort of like back of word, basically. If you see in the sentence the word not, the feature will have 1 here, and if you see the word bad, then the other feature will be there. So if we have, for example, not and bad in the sentence, our feature vector will be 1, 1, 0. Okay, makes sense? So we're basically projecting to three dimensions. All right, so this is good. Now I took this sort of a plane here. Can you visualize that? So we have 3 space, and I put a plane on top of this. Projected this on the plane just to see this example. Now, so this is basically bad means 0, 1, 0. Good is 0, 0, 1, and so on. Okay, so we have this map. Good. Yeah. Okay. Now we have the problem. If you want to classify sentiment here as a positive or negative, can you draw a line here in between that will separate positive things, so bad and not good, from not bad and good, because these are sort of similar or same. They carry the same meaning. So can you make a line here that separates positive or negative? So this is positive, positive. This is negative. This is negative. Can you do that? And the answer is no, obviously, because I want to showcase like the XOR. So it's a real thing. It can happen. I mean, even like this in this simple example, you need some nonlinearity to learn this function in this simple vocabulary. Okay, so you need to learn some sort of maybe this function somewhere, some nonlinear function that will map these words. Okay. Any questions? All right. So let me introduce you to the multilayer perceptron. As I said, we just built a deep learning, the first deep learning network, deep neural network. And here's again just a summarization as a full computational graph. So again, we have the input here and the first hidden layer. So this is the hidden layer. Here we have the nonlinearity. Right, so we have the G function, which could be ReLU, for instance, or others. And then we project it to this in this output layer. And typically the output layer is followed by a sigmoid or a softmax. So again, sigmoid for binary task and softmax for multi-class problem, right? So what is this thing? What is it? L, yeah, loss function. Yeah. So we have the loss function, and this is again what? Yeah, the goat label, exactly. Oops. Label. Nice. So this is the full computational graph of multilayer perceptron, a deep learning architecture which can solve not only like XOR problem, but depending on the width of the middle layer, of the hidden layer, it can solve much more. Actually, all functions if this is wide enough, but you don't want to do it wide, you want to do it more deep, so stacking more layers. Okay, and so can we train this from data? Yes, yeah, we can train this from data. This is what we did yesterday. Or we kind of finished before doing this yesterday. So we have this, we have a backpropagation for learning gradients. So what we need to do is just to find the gradients for each parameter. So we need to find partial derivatives of the loss with respect to this, partial derivative of the loss with respect to B1 and here. So these are we are optimizing the parameters. This is given for a certain data point. This is given. So we have growth labels and the input here. We're given that for each example. So we're iterating over data set and take each example, and then, or a mini batch. We take each example and compute the loss. And then either we do it online. So for each example, we're updating the gradient, updating the weights given the gradients, or we do the average over the mini batch, which we had in the last lecture. So we should also maybe try to implement that as well, but it's unnecessary. So basically you are able to implement it. So you can learn the parameters of this function to solve a task, which could be more complicated than a linear function. Could be any nonlinear function. Actually, could be any function. Okay? Any questions? So once you train this, where is the prediction coming out? Where do you predict the class? Where exactly will be the output? So you train the model already, so you have the weights and biases already trained, and you have a new instance, new example, which you haven't seen before, and you want to predict the value. So where this will come out here in this graph, the prediction. Yes.
The error that comes out of the softmax.
Here, exactly. Here will be the output, like prediction, right? Because the loss and the goat label is just for training, for finding the best parameters, so minimizing the loss. Once you train the model, the prediction is coming out of here. So the prediction will be, in case for softmax, for example, a probability distribution over your classes, maybe. Okay, cool. So this is multilayer perceptron. Any questions? So let's move on. So today, I mean, we spent some time on that, but I guess it's important to kind of really dig deeper and connect all the points you had so far. So now you know deep learning, so to say. You know how to build multilayer perceptron. And very many things are, including transfer models, are basically using multilayer perceptrons in their architectures. There's other tricks in there, but the multilayer, fully connected layers and multilayer perceptron is a thing. Okay. And it's been here for a while, from the 60s maybe. But well, it was just a perceptron on multi-layers. So the layers were hard to train, and we needed some tricks to learn it better and faster. So we're gonna move to language models. Okay. So who has heard of language models? Language models. Anybody heard the word language model? Yeah. In which context? Large language model, right? This is like, today is like, nowadays we have large language models. This is like LLMs. This is the cool word. Okay, large language models. So now we should understand where this comes from, and why large language models work as they work, and what tasks are they trying to solve actually, and what not. And I think we should start a little bit in the precursor of the large language models, the neural language models, maybe with small language models, but the principle is similar. So for language modeling, we need some probability. Okay, so I asked you in the first exercise, how's your probability theory? And everybody will say, yeah. Okay, so let's see. Hey, good morning. So what we're gonna work mostly with, it's a few simple contexts. So we're gonna have categorical random variables. So we're gonna have something which might have some probabilities. So we call them random variables. And an example would be the first word in a sentence. So the W1 here. So don't confuse this with weights in neural networks. So we are in a little bit different world now. So this is a random variable which we use capital letters to describe, and they are ranging over the whole vocabulary. So we have a fixed vocabulary, and they're taking one of those values with some probabilities. Okay, so categorical random variable. We have it's not like it could be mapped to discrete, and if you're coming from measure theory, well, do your math behind that, but it's not important. I mean, we have just categories and they have probabilities, right? So then we have a probability distribution over random variables. So for example, we know or might kind of estimate what is the probability of the word V at position 1. And since we have this random variable for the word at position 1, so the first word in a sentence, we kind of said it's going to be W1. Then the probability of word at the variable taking the word V, so one of the outputs, might be some number between 0 and 1. Okay, so we just have probability distribution over discrete data. Any question to the terminology or notations? So is it clear? Like we have categories and they have probabilities. Like a softmax. Okay, softmax is the same thing. You have a vocabulary and you put a probability distribution over vocabulary, maybe, or over your categories. Okay. So they should sum up to 1 and all the stuff with the probability distribution. All right. We also might be here in this, misusing notation, because this probability function is also typically, so this is one way of writing that the variable is taking a value, but we also use just a capital P instead of PR, or we're writing P with the actual value and stuff like that. So here, like, the notation is really misused quite a lot. So you should check your kind of understanding that what you understand as a random variable and probability distribution matches what is here. Like if you're coming from, as I said, from measure theory, like there is much more layers of abstraction behind, but it shouldn't be. We were trying to make it simpler, not more complicated. So basically, this is the probability of the word at position 1. This is probability of the word at position 1 being the. Okay. Okay. So then we have this thing called joint probability. So let's have two variables. So one is probability of word the at position 1 and probability of cat at position 2. And this is what is this symbol? Anyone remember this symbol from mathematics? Yes.
I don't know the English word, but
say it in German.
So thing in.
Yeah, exactly. It's intersection.
Oh yeah, intersection.
Intersection of sets. because these things are sets and events and stuff like that. Doesn't matter. So this is one way of writing this intersection, but we'll use better notation with just comma, as I show later. But basically, this is saying the joint probability. So the first word being the and the second word being cat is something here. Okay, so this is a notation. Usually we use this sort of notation, so we use comma here. Okay, and now since the intersection, like you can shuffle things around, this is the same as this one, right? Because there is no ordering of the random variables. This is what we made. So these two things are the same. There is no ordering of these variables in the joint probability distribution. Make sense? All right. Now, the last thing, I guess, as a refresher, is a conditional probability. So we use this, I don't know actually how this symbol called. I call it the pipe from Linux, but maybe there's a colon, maybe? No idea. Do you have a German word for that? Yeah, I have no idea either. Bar. Okay. Bar. I call it a pipe from Linux, but it's absolutely wrong for mathematics, so don't call it like that. But so we have the bar. Okay, bar is not. Makes sense. So we have here that the probability of cat at position 2, right? So position 2, word at position 2 equals cat, given that we have at position 1, the word the it has a definition. So this is like the definition of conditional probability. So you take the joint probability and divide by the marginal. Okay, so this is something you might have seen. You found it? Pipe. Oh, okay. But in probability theory or just a website? ChatGPT told us it's pipe. So I don't know. Make your choice. Anyway, so this is the conditional probability, and this is how we compute conditional. This is definition of conditional probability. Okay, so everybody's happy with conditional probability, joint probability. That's great. That's great. So we're on the same page. Then independence. So two variables are independent if and only if their joint probability is a product of their marginal probabilities. Okay, so this is independence. Cool. Okay, interesting. And we have also conditional independence, but I don't think it's important for today. So there is, okay, there are x and y are conditionally independent given another variable if and only if their condition joint is a product of their condition marginals, something like that. But I don't think we're using conditional probability here. But the independence is plays a role. Okay, so this is a refresher. Everybody should know that somehow because you had like a stochastic for informatic or something like that. Okay, cool. Great. So now we know probability theory, and that's enough. You don't have to know anything else. Yes, there might be an error. Yes, where's the error? This should be y exactly. So let me just write this. Okay. Or you can fix it on GitHub and just I don't have to fix it later on. But okay, thanks. Absolutely. All right. So we have probability now, and let's move to language models. And I'll call them classical language models because they were precursors for the large language models, for narrow language models. But the assumption they're making and also the task they're modeling remains pretty much the same, as we'll show later. Okay, so that's why it's important to understand where it comes from. So the goal of language modeling is basically assign probability to sentences in language. So the example would be, so the task, I have a language model, I wanna ask it, what is the probability of seeing the sentence, the lazy dog bark loudly? And my language model should give me a probability of this sentence. So I have a language, which is maybe English here. I have English language model, and I wanna know what is the probability of seeing the sentence, the lazy dog bark loudly? Or another task we want to ask, which is the same task in a little bit different setup, assign a probability for the likelihood of given word or a sequence of words that follow a sequence of words. Okay, so we want to ask what is the probability of seeing the word bark after seeing the sequence, the lazy dog. So what is the difference here? So here we are asking for for a joint probability of all these words. And here we're asking, right? I mean, we're asking what is the probability of W1 equals D, W2 equals lazy, and so on. And here we're asking, so what, this is the question. Here we're asking what is the probability of 1, 2, 3, 4. The word at position 4 equals barked. What comes next? Which symbol come next? The pipe, yes, let's come to pipe. Given that W1 was D, W2 was lazy, and so on, okay? Well, because you know what is the conditional probability, you already know that you can compute the conditional probability from the joint. So basically, this is the same task, but you're just asking different questions. Here you ask for the continuation. What is the probability of barked after seeing this? So it's conditional probability. Here you're asking for basically the joint probability of everything. But you can compute the conditional from the joint, given the definition of the conditional probability. Okay. Any questions? So this is what we're asking the language model to do. We're asking what is the probability of a sentence, or if I have a part of a sentence, what is the next word? So what could it be good for? Like this, for example. This is a nice example. Like, can you use it for some meaningful in a meaningful way? How can you use the language model for your whatever you do in your life?
So it could like predict text. So if I want to write something, it could make offers.
Yeah, it predicts a text. So everybody's using that basically on your smartphone. Like, how is it called? Like smart completion or something. You write a message or WhatsApp, and then it gives you suggestions for the next word. Yeah, most of the time they make sense because they're generated by a language model. So you write, I want to go, and the next word would be, well, maybe it's personalized. So for me, it would be like home. Maybe for you, it would be a pub, something like that, you know. But I want to go to the pub, or maybe home as well. I don't know. So it's basically suggesting the next word. Yeah, this is very useful. So this is basically behind all these completion is a language model, nothing else. And previously, they, you know, if you remember, maybe 10 years back, like there was not. They had like the T9 completion, right? I do remember that. So it was maybe like these simple classic language models. Nowadays, it's more like neural language models since the last 10 years, maybe, or 6 years. But this is it. So what's the, you know, it gives you basically a probability distribution of the next word. It's very useful for completion, or ChatGPT does the same thing. It's basically generating word by word and predicting, given the previous context, predicting the next word. This is it. This is language modeling. Okay. How is it done? It's a different story. But the task is the same. Just predict the next token or the next word given the previous context, or probability of the next words. So here formally, okay, so we have a sequence of words, W1, 2, and so on. And we're using this notation. Okay, so this is a sequence of words. So this is the notation. And we're saying the probability, okay, this is just the same thing. So we're using this notation with a colon. It's a simplification for sequences. It's kind of like in Python. So indexing arrays in Python, you also use this colon here. And again, so we usually don't write a full, you know, W1 equals this and so on. We just omit the W's. So we're saying, oh, yes, we're kind of assuming this is clear from the context, right? So we're just writing the words. What is the probability of a sequence of words without saying, okay, yeah, there's a random variable at position 1 which takes this value. So we just make it simple. But remember, there is some formalisms behind. Okay, so we have this joint probability. So this is the joint. And we factorize the joint probability into products. Okay, so why can we factorize joint probability to a product? This is an important thing. Well, how can we do that? So there is one type of factorization. I mean, you can factorize joint distribution into many different products of conditional distributions. You can do right. I mean, you can You can do it in many different ways. We don't have time to spend it here, but there is one factorization which is useful, and this is left to right. So what I'm going to do is I'm going to express this joint probability as a product of conditional probabilities. And I'm taking that, I'm saying that I'm starting with from the left-hand side. So I'm taking, so this is what could be the S? Okay, this is a good question. What is S? We didn't define it. What is S? Yeah, it's a special symbol, and it's like a start of sequence or sentence, sequence token. So we added an extra S, the cat said, right? So this is saying, okay, so what is the probability of seeing the first word given the start of the sequence times the probability of seeing the second word given the sequence and the first word, seeing the third word given the previous context, and so on. And this is equality. I mean, obviously, if you multiply these together, by definition of conditional probability, you get the full joint. Okay? Everybody's with me? Any questions? You can do it also, you can factorize it in many different ways. You can start from the back. You can say, like, well, okay, I'm starting, what is the probability of the last word given something else, and what is the probability of something else given something else? As long as the conditional probability holds, then you can do different factorizations, so to say. So factorization means a product of parts of vectors. So this is one useful factorization. So why is this useful? Well, why do we do it like left to right? What is interesting about, for example, what is the meaning of that? Why do we do it left to right? So yes.
Because, for example, when using auto completion for our text, we need to have the probability for a third word at the third position. We don't need the probability for the last word first. So we just do it in the way we can use it.
We do it in the way language works. Language works linearly from left to right. So you basically, you only see the history, which is the first word and second word, and you can predict the third word. It wouldn't make any sense to predict, given the first word and second word, to predict the fifth word, and then given the fifth word, first word, and second word, to predict the third word, and vice versa. It makes no sense. So language is left to right. So you take some previous context, and given on this context, you condition the next word. So it's really left to right. Right to left, I mean, now there's languages whose, the writing is right to left, but basically it's still linear, like you think on left to right a little bit, like in time, basically, evolves in a time. Okay. So you're predicting the future given the history. You don't want to predict the history given the future, conceptually. Okay. Now, oh, why is this missing? Okay, anyway. Now, the thing is, we did factorize these things. So this is easy, this is short, this is two words, this is just a start, this is one word and start, this is two words and start, and stuff like that. But, well, okay, we still have this large conditional probability, or long in terms of the history, where we take, again, all the words and predict the last word. So it didn't help us at all. Because now the last word still depends on all the previous words in the sequence, right? I mean, we take the start, first, second, up until the previous word. I don't want to predict the next word. Yeah, that's bad, because you're conditioning on all the previous stuff. So sometimes we can make stuff easier, and okay, because why this will be a problem? Because we need to somehow estimate these probabilities, and we'll be estimating the probabilities from data. And this long context will cause us some issues, as we will see later. So we want to make it shorter. Let me see, do I have how to estimate it? Yes, okay, so we'll see in the next slide why this is an issue. We make one assumption, and we say that, so Markov assumption. Anybody heard of Markovian stuff? Okay, so what do you know about Markovian stuff? You're nodding, yes.
So at the Markov chain, where they just depend on the last one.
So you had the Markov chain. Where was the Markov chain, in which course? Oh, okay, in stochastic. So this is it. So basically this is it. So Markov chain means you're only conditioning on something in the chain of probabilities. You're conditioning on some limited context window, not on all the variables in between. So this is the same thing. We're saying the next word depends only on the last k words. So we take the last k random variables and we limit the context. So here this is approximation, right? Because this is not equality. We're approximating. We're saying, okay, well, let's not take the whole sentence. Let's take last 3 words maybe and predict the next word. Maybe it's good enough. So we're approximating. Okay. So here's an example. We have the cat sat on the something, and we want to predict what? We want to predict the next word, the 6th word. So what is here? This is what you want to predict, given the context. And we're gonna take a second order Markov model, which conditions not on the full sentence, like all the tokens and start, but only the 2 previous ones. So we just take on the, and then predict the next word. Okay, so this is our assumption or our simplification of stuff. Is it good or bad? Will it work? Will it not? What do you think?
In this case, would be way better in new words, because that
for this example it will have difficulties to predict what is the word? The cat sat on the, I think the original, on the mat. But if you see on the, what is the next word? On the, I don't know, on the road, somewhere on the table, but not on the mat. It's very unlikely. So the context here is limiting us. So this is our assumption. But in some cases, it's really good. Like just, you know, second order, like, yeah. I want to go home. Want to go home. That's 3 words. So something like, some phrases are basically local, where you can really, you know, enough context, like 3 previous words can give you like good hint about the next word. So in some cases it will work well. In some cases you need large context. So we call this long dependency. So in some cases you need a long dependency to understand what the last word would be, but in some cases you need just a few words before. So it's an empirical question. And also the problem here, another problem, it's like a design choice. Because we need to find these probabilities. Okay. I showed the answer, but I want to ask you anyway. So pretend you didn't read it. How do you estimate the probabilities of things? In general, you have things, something, you have a model or a world, you want to estimate a probability. How do you do it? You want to estimate a probability of, I don't know, like tossing a coin. Now it's fair, but something like you have an unfair coin, which means it will fall on heads more likely than on tails, and you want to estimate the probability of this fall. How do you do it?
We do it 100 times and then we take the average.
Counting and dividing. You count exactly. You do it 100 times or 1,000 times. The more you do it, the better estimates you get. The more data points you have, the better estimates of the probability. And then you count the successes and divide it by the number of everything. So it's estimation of probability. It has a name. Do you know the name of this counting and dividing? You heard it? So it's called maximum likelihood estimation, MLE. And this is definitely counting and dividing. So how do you do it with words? Well, you do it the same way. So how do you estimate the probability of word at position I being W given the context? Well, you just count the number of words. So this is words like the cat sat on the mat, and divided by the cat sat on the, how many times you see the cat sat on the mat? Sat on the mat. How many times you see the whole sequence in your data, divided by how many times you see the cat sat on the, okay? You just count and divide. So now you see the issue here, why we had this. Any questions? Or is it all good? Now you see, what is the issue now? I mean, we now see the issue of the context, because how many times you think you will see, okay, where do you get the data from? So you take Wikipedia or you take the internet. You take basically a corpus. It's called in linguistics, it's called corpus or text corpus. And it's just a plain text. It's just news articles, whatever, books. So you got billions of words, billions of tokens. And you count the number of occurrences of the cat set on the mat. So how many times do you think you will see the cat set on the mat? Maybe not at all. But I mean, this is like very, yeah. Exactly, yeah, exactly. As many times, because this is like an example every linguist is using, so you're gonna see that. But the dog set on, I mean, how many times you will find a dog set on the mat? I guess maybe not at all. Like the dog set on the dog set on the mat. Yeah, maybe. I don't know. So this is the issue. Like the sparsity of the language. You know, you won't really encounter so many. So that's why we do the simplification of the Markov model. Sorry, of the Markov assumption is limiting the context, because you have much better chances of seeing something, a phrase which is shorter than something which has 20 words. Okay. The question is now, okay, we're estimating this probability. So what if you actually never see this? So you never see the cat. Let's make a dog. The dog. You never see the dog set on the. You never see it in the corpus. How do you estimate a probability here? So what happens here? This will be 0. So you cannot divide by 0. What do you do? A simple trick. What do you do just to fix this? You don't want to divide by 0. So you say like, I didn't see that at all. What can you do to fix that? Everything is 0.
The probability that is...
Yeah, the 0 probability are kind of bad, because this sentence, like the dog set on the cat, it has a probability. It's a valid sentence, so it shouldn't have like 0 probability, right? Yeah, it's a sentence in a language.
Probability that will appear.
We want to no. Okay, so this is interesting. So we want to build a language model. So a model that understands language, and whatever you type in. Whatever you are in the language, whatever you type in, will give you probability of the next word, even though it hasn't been seen in the training data anywhere, like in new sentences. The way to build this model is to train it on existing. I mean, you can write down the probabilities by hand. You can say, okay, the probability of Matt given the dog set on the will be 0.0. No, you don't want to do it. You want to train it from the data. So you estimate it from the data. So it's an estimation, right? It's not the true probability distribution. It's an estimation. Okay, so you don't want to have, I mean, all sentences might be like small probability, but not 0 probability. Like what would be like well, maybe this sentence should have like 0 probability, because it makes no sense in the language. Like this is bad. But some meaningful sentences, like the dog set on the mat, why not? You want to pretend 0. So another solution to this. If you have the slides open, there is an answer. So don't spoil it. Yeah.
Question back. If I don't have this sentence, where did I get the sentence on top? But the second one is the subset of the first one. So where did I get the?
No. Oh yeah, that's true. Okay. That's true. Yeah, if you don't see this, you don't see this.
Yeah.
That's true. Yeah, so you end up with 0 anyway. Okay, so it's not like dividing 0, it's like a 0 anyway. So if this is 0, also 0. So you don't want 0 probabilities at all. That's true. So there's a trick you're gonna do. And it's just pretending you saw it at least once. Interesting, yeah, I saw it once. Okay, so alpha typically is 1. So you add one smoothing, and here you add 1 multiplied by the size of the vocabulary to have some better properties of this probability distribution. So this is a trick. If you're estimating the counts, you say, oh yeah, I just add 1 and that's fine, because then you will guarantee that no sequence will have 0 probability. But if you don't see it in the training data, they will have like very, very small probability, but not 0. Okay. If you ever, anyone had like Bayesian networks, Bayesian probability theory? Okay, no. So it has a reason why it's called like that, alpha smoothing. But this is a trick that works like in the counting models. Okay, so this is estimating the language model. So you now understand like why we need to estimate the probabilities and the trickiness of being zero probability. So we want to avoid a zero probability. So in this case, even like the would have like very small probability, but some meaningful sentences will have higher probabilities. Now let me just see whether we finished this. Yes. So 2 slides and coffee break. Okay. Sorry, no, a break. So, okay, how we evaluate? So we learn a language model, we train it on data, we train it on Wikipedia, and I want to evaluate how it works. Because some models are better than others. So how can I evaluate? So language model tells us the probability of sentence S. So we want to have this. So let's have a test corpus. Okay, interesting. So let's test corpus. What do you have to remember? So your test corpus and your training corpus. Is there any requirements on that? The basic rule of thumb. You cannot test on the training data, exactly. No, no. I mean, you can, but it's not evaluation. Never touch your test data. So you take Wikipedia or you take the internet and cut part of that and keep it aside. And this will be your evaluation corpus for language models as well. Okay, never touch that. Never evaluate on your training data. You know why there is such issues with ChatGPT and stuff like that doing evaluation on stuff? Because you don't know what's in the training data. So maybe ChatGPT saw like pretty much all the tasks which we are trying to solve. So that could be like seen already, and then you're cheating. So you have to. We don't know what ChatGPT used for training. So this is really, from the scientific perspective. So you have a test corpus somewhere in a safe. And it has n sentences, and each of them has a uniform probability of appearing. So each sentence has a probability 1 over n in your test data, right? You have 100 sentences, and each of them appears different sentences. So each of them appears with 1% probability. Okay, so this is interesting. Then we can use the cross entropy from last lecture. So no, the cross entropy of our model is. So this is the probability of the sentence, and this is the probability from the language model, and this is the definition of cross entropy. So we're basically summing up for each sentence in the data. We're summing up this this cross entropy. So let's do a little bit of math. So we move the n forwards. Okay, this looks great. So can we do anything else with the logarithm? I guess we can. Logarithm of reciprocal is a minus logarithm, so I guess we move the minus here. Okay, yeah, that's what we do. So minus 1 over n and sum of the logarithms. So this is very same what we did with the cross entropy last time. And that's it. So, and this is cross entropy, and then how we actually evaluate the model, we use the perplexity of the language model, and it's 2 to power of cross entropy. So 2 to the power of this formula. Okay, so this is perplexity. And it's saying, in a way, how sure or unsure the model is for predicting the next word. So the lower perplexity is better. Lower, better. And you can guess why, because of that. Like if you do the math here, you see like if it's if you're getting high probabilities for the sentences you see in the corpus, then high probability of taking a logarithm of high probability goes to. So we have a log. There is 1, and this is log. So if you're getting higher probability, the value goes more to. What is the logarithm of 1? 0. What is the probability of 0.99? Almost 0, something like, yeah. So it means if all these probabilities will be 1, so the model is saying, I know exactly this is probability 1. I know this sentence already. Then you end up with 0, and the whole thing will be 0, and 2 to 0 is some number. So, that's why the model should assign high probabilities to sentences which actually appear in the language, and that's why you get the lower cross entropy. Excuse me, the lower perplexity, as well as cross entropy. Okay, and this is the perplexity of language model. So it's saying like, on average, how many words could be confused in the next prediction, something like that. But it's not really important. So the lower perplexity, the better, and that's how you evaluate it on the test data. Okay. Yes.
Why do I take the exponent? Is it to linearize the
That's a great question. I would like to answer it, but I don't know the exact answer to that. I mean, somebody came up with this definition, and it has to do something with to change the logarithm base 2 best. So this is log base 2 mostly, to take it back somehow in a way, but I would have to look it up. I'll look it up. I don't know. Okay. Any other questions? So this is evaluating the model. So the shortcomings, we already talked about them. And these are the long-range dependencies, absolutely. So the capture dependency between the next word and the word 10 positions in the past, we need to see a relevant 11-gram in the text. Okay, this is also like, why is it called n-gram language models? Because we are counting n-grams, right? We are counting bigram. Bigram is 2 words. Trigram is a 3 words, and so on. Okay, so it's n-gram language model. And if you want to capture position, capture dependencies between like a very beginning of the sentence and very end of the sentence, like 11 words, you would have to have a 11-gram language model. Yeah, I mean, you won't build 11-gram language model because the number of parameters. You need to estimate all 11 grams for all words to see them in the training data. Forget it. I mean, you have no chance to estimate anything meaningful. So in practice, it used to be like trigram or 4-gram language models or their combination, maximum. And then they like generalization across contexts. So if you observe black car, so you see it in the training data, and the blue car, but it doesn't influence our estimates of red car if we haven't seen it before. Okay, it doesn't really generalize because you know what's the probability of these things, but if you never see a red car, you have no guess about the probability. It doesn't generalize across contexts. This is like the shortcomings of this. Okay. Yeah. So having said that, any questions to classical language models? So you can build it basically in an afternoon. You just take a corpus, counting and dividing, and you get the probabilities. That's it. You can build really a simple language model by just taking a corpus from the internet and counting the number of occurrences of maybe bigrams or trigrams, and you get a probability distribution of each of them, and you build a language model. So you can ask, if I see these 2 words, what is the probability of the next word? You can do that. That's fairly conceptually simple. The trick is how to make it robust and to overcome the shortcomings, okay? So let's make a short break, 7 minutes, 7.5. So we'll start at 45. So now you might be asking, what is a better way? So why is language models and why counting-based language models? Yeah, why? So we have these shortcomings. Can we make it somehow better or more robust, or maybe taking larger context into account? Because if you're familiar with ChatGPT or other large language models, there is this things called context. So you by basically paste, you type in some text, and it takes much longer than just last 3 words for predict the next word, right? So it takes the whole document, or like 3,000 words or 10,000 words or whatever, right? So we need to fix that. So of course we have narrow language models, and the idea is the same. So how we build a narrow language model? So again, the task is to predict probability of the next word given the previous words. Okay, so we want to predict probabilities. Oh, interesting. So we want the probability distribution over the vocabulary for the next word k+1 given a k-gram of previous words. So we want the probability distribution. Okay, so what does it mean? We have vocabulary like a, the, I, and stuff like that. So this is our vocabulary, and we want a probability distribution for the next word. So what does it mean is that we have sort of like a histogram of probabilities, something like that. So this is a histogram, right? So these are the probabilities, probability distribution over the vocabulary. So for each word, you want to say what is the probability given the previous words. So can we build a neural network, because now you know what is a neural network, that predicts a probability distribution over categories? Can we do that? Do we have enough knowledge now to build something which predicts a probability distribution over some categories, classes? So we're classifying a text. We're taking this as the input and try to classify which word is the next one, which belongs to the previous one. This is a classification task, basically, right? We're classifying which is the next word. We're saying to which word it belong, does the previous context belong. So we're building a classifier in a way, and the number of classes is, how many classes is in there? How many classes is in there? I mean, we have the vocabulary, so how many classes are we classifying into? Yeah, size of the vocabulary. So we have lots of classes to classify into. That's fine, we can do that. Nothing is preventing us to do so. And we want the probability of each word being the next word. So we want the probability of each class. So we want to build a model that predicts probability distribution. We have a function that is doing so already. So what is taking something and creating a probability distribution? The softmax, yes, yeah, exactly. So we have we can take anything, some sort of input of size, larger size of vocabulary, and just put a softmax, and the softmax will create a probability distribution over words. So we have we know softmax, we know how many classes in there. So the classes is the number of the words in the vocabulary. So we have the input. Well, the question is how to model the input, because it's a couple of words. Oh, how could you model the input? We have a couple of words. How is the input to the network? Because now I can use the word network officially after today's lecture. What is the input to the network? We have a couple of words. So how can we model the input for the network? We have it already as well. How can we model the input? We have a couple of words. How do you want to model it? How do you turn words into a vector, into a feature vector?
Like having one in the vocabulary. We choose a vector as long as the vocabulary and put a one for the words. Yeah,
there's a word for that. It has a name. You're on the right track. It has a name. Back of words. Exactly. So we can use back of words to model the input. Okay, cool. So let's try to move, to take these words, create a back of words, and then build a classifier, which in a way it's predicting the next word. But it's basically modeling, given the context, how do I classify the context into the word? I'm building a classifier. And the classifier is giving me like a softmax probability distribution. In principle, is the same thing as a classifier into size vocabulary classes. But what I'm saying, well, it's what is the probability of the next word? But basically, I'm building a classifier. I'm saying, yeah, given this feature vector of the input, what is the most probable class of the next word? Okay, that's doable, right? So we can we build it? Yes, we can. Yes, exactly. No, that's true. I mean, we can build it. We have everything to build this. This is just, conceptually thinking differently. No, we're not counting and dividing probabilities. We just say, yeah, we have an input, and we want to predict probability of the next word. So our number of classes is just the size of vocabulary. Fair enough. And where do we get the training data for that? So we want to build this model and train this model. Well, we don't have the model yet, but we have it conceptually now in our heads. Where do we get training data? Because I'm classifying things into words. How do I get the training data? So I need features, and I need a label. Oops. How do I get it? This is my training example. Where does it come from? Any ideas? Yeah.
We can take a data set of text.
Mm-hmm.
Many n-grams or k-grams after each other, essentially.
Yeah, exactly. We just take a plain text. We take, for example, here, we take the sentence and say, okay, this will be the feature vector. This will be the so-called class, but this isn't like the next word. And we have to change it into the feature vector, so maybe back of words, maybe. And that's it. We have a training example for free from the text, just like that. And we do it. This is the same as counting and dividing. You take Wikipedia and create your training examples for free. So basically, you don't have to create any manual labels. You just take what's in there and you pretend the next word is basically the class, which you want to which you want to predict. Okay, does it make sense? We just get data. We get training data for free. We don't have to label anything. We still have a classification task to solve because we want to predict the probability distribution over the next word. But we take data from just plain text. It's the same like for counting and dividing, like the count-based language models. All right, so let's build a thing. Yeah, so there's one thing. We have an embedding layer. Did we have embeddings in the last lecture? I guess so. We talked about representations, and we talked that each word is can be represented as a dense. So each, let's say, one hot word, it's getting a representation in a low dimension. So we had this word to languages mapping. We had six languages and 50,000 words, and we're talking about like how you can actually represent average back of words in two different ways. So there is the inputs are symbolic categorical features. So because words are distinct categories in a vocabulary like 50,000, so there's only one of them, and these are distinct, but we associate them with a dynamical vector for some d. So you will see later what it really means, the embeddings, but this is somehow connect the last lecture on representational learning. And these vectors will be parameters of the model, so we will train them. It will become much clearer what I mean by that in the example. So the embedding layer. Okay, this is interesting. Okay, let's spend some time on that. So the mapping from a symbolic feature values such as word number 48. So what is word number 48? We have the vocabulary, and we have the words, and number here is like a position 48. Okay, so this is the category, and we want to map this one hot vector 0, 0, 0, 0. Here's 1, and here's zeros into a dimensional vector. We want to make it somehow smaller, typically. So this will be size 50K, and D could be maybe 300. Okay. So this embedding layer is going to be a matrix of size of the vocabulary times the dimensions, and each row corresponds to a different word in the vocabulary. Okay, so then the lookup operation is indexing. So we're saying, so this is the V operation. The V operation of the word is basically taking a row in the matrix. And if the feature is a one-hot vector, which we have in the vocabulary, then the lookup is implemented as the multiplication. Okay, I hope I have an example here. No, let me make one. So I have some matrix here, W, which is, say, size of the vocabulary. So this is V, and here this is D, right? And there are some numbers which I'm going to learn in a network. So this is like parameters of the network, doesn't matter. Then because this is the size of the vocabulary, so each word maybe like at position 48, I can just look it up, just take this row, and this is how I'm going to represent the word. Not as a one-hot vector, but as a row from this embedding matrix. We had it last time already, if you remember. We are just taking, so we had this vector of 0, 0, 1, and 0. And if you multiply this row, sorry, this vector by this matrix, what you're actually doing is just taking the row where this is 1. So this is why this lookup operation is basically multiplying the vector, which is one hot, by this matrix. We call it A as embedding matrix, but conceptually is the same as the W matrix. Okay, so you have a word, which is categorical value, so one hot encoding of a word, and then by multiplying this by the matrix of embeddings matrix or the weight matrix, you get a dense representation of this word. Yes.
Why isn't this matrix dimension B cross B? Because they have as many categories as words as I understood.
Exactly. You can, so you can, so the D, you're asking why the D is not, why D is not the same as a number of categories, right? It could be anything. Because what you're learning here, or what you're trying to do, is a projection to some other space. So you're projecting from 50,000 dimensions into some other dimensions. And empirically, you want to project into low dimensional space, because in this low dimensional space, and this is like where the embeddings actually are important, in this low dimensional space, maybe words that are distinct in your vocabulary, like great and good, they have what we call about the Hamming distance. They are just one. You know, they have no relationship whatsoever. From the vocabulary, you don't know there is a relationship between good and great. But maybe if you have a clever projection into this low dimension space, these two words can be maybe closer together. So good and bad. So you can imagine even like projecting into two-dimensional space. Let me just write it here. So you have a good and great in your vocabulary. And this will be 0, 0, 1, 0, 0, 0, and great will be 0, 0, 0, 0, 0, 1, right? There's no whatsoever similarity, nothing about meaning at all. These are just two distinct things. But you might want to find a projection, like this embedding matrix, that if this will be dimension of V times D, where D is 2, so 2 dimensions, a plane, these two words might end up close to each other and maybe far from, this would be like a bad. While in this vocabulary, bad would be maybe 0, 1, 0, 0, 0, 0. So there is no notion of similarity of any meaning, but you might have projection, and you might learn that this projection that puts these words maybe closer together in one space. So they will have some better properties. Okay, does it make sense? I think this is actually an important example maybe. So you want to learn good representation of words, such that the words are somehow maybe close to each other if they have similar meaning. What does it mean, similar meaning, close to each other and stuff like that? Everything needs to be defined. But conceptually, you want to learn better representation of words than just one-hot encoding. Okay? Does it make sense? Any questions? So this is what we conceptually want to do. This is how we technically do it. So we have some weight matrix or embeddings matrix, which we are, when you multiply the one-hot encoding by the matrix, you're basically doing a lookup operation on this matrix, right? Because 0 times first row, 0 times first row, 0 times first row is 0 plus 1 times this row plus 0 everything. So you just basically look it up in the matrix. But you can implement it as a matrix, vector matrix multiplication. Everybody agrees on that? Okay, cool. Why is multiplication better than just iterating over stuff? Why is multiplying a vector by a matrix better than doing like for loop and I don't know? Yeah.
I think most of the processors have special operations that they can do that in an instance.
It's easily parallelizable, and then it's much easier to write a gradient of a multiplication of two things, the partial derivatives. I mean, this lookup operation, you can write the partial derivatives with respect to everything because it's just a product. So you know how to do derivatives of a product. So you can stitch it into your computational graph. But vector matrix multiplications is the key. So it's fast. Okay. So when we talk about how to solve this problem, we said, okay, we know here softmax, this is great. We know features and label, and we said we use back of words. Well, we might do something even much simpler than just back of words. If we have 3 words, so we have the black dog, and want to predict the next word, we can, okay, what we're doing here. So this is a computational graph. Let's have a look. So we want to first, for each word, we want to find its embeddings, so its embedding vector. Okay, so this is exactly this operation. So for each word, which is represented as a one-hot vector, we want to find a low-dimensional vector from the embeddings matrix. Okay, this is what we want to do. We do it for each word. So this is the previous context, the black dog, and then we are looking for the next word. So we take each word and perform this lookup operation, which we just defined on the previous slide. Basically, it's the multiplying the one-hot encoding of the word by the matrix of embeddings. Okay, so we multiply V and E. We multiply one-hot of black with E, and we'll multiply the dog by E, which will give us a single vector for each of those. Okay, so this lookup. So if we have the embedding, the embedding matrix is the size of vocabulary times 50. Okay, so the E matrix, which we had here, so this is size of the vocabulary, and the D would be 50. Then the output of this operation will have size of 50, exactly. We're just selecting one row. Okay, so which means each lookup output, so everything what's coming out of here, this will have a dimensionality of the embeddings of 50. So this will have a vector of size 50. And here, the same thing, 50, and here also 50. Okay, you know why? Because we're just selecting one row from the embedding matrix. How we do it is by just multiplication, but it's just a technical detail. Okay, so this is how we do the lookup. Well, okay, now you might be asking, why do we have the same parameter for multiple nodes here? Why do we have this for multiple nodes? Why don't we have like E for the first word, E for the second word, and E3 for the third word? Why do we have like a one matrix for all words? So is it better? I mean, we could theoretically have E1 here, E2 here, and E3 here. We can have that. We can have 3 matrices, but we have just one and share it. Why? Okay, storage reasons. Why storage? What's the size of the embedding matrix? It's huge. It's huge because it's like 50,000 times 50, and all is filled with numbers. So it's gonna be huge. Okay, so memory reasons. You don't want to have like 3 matrices. There another reason?
Well, we also don't want the semantics of the values to change depending on where you put it.
Exactly. We want the representation of the word in this low-dimensional space. We want these representations not to be depending on whether you're in the first position of the sentence, or the second position of the sentence, or the third position of the sentence. You want to learn sort of a context-independent representation of the word. Okay, so we don't now, in this case, in this neural model, we want to have this embedding matrix for each word to be completely context independent. So each word will have a projection, and we want to share this. I mean, we want to learn this for every word, and not depending on where you are in the position of this sentence. Okay, so this is a design choice. We might have multiple embedding matrices, but now we have just only one because we want to learn for each word just a single embedding vector. Okay, so this is the idea. We learn embeddings for each word. Okay, all right. So now so up until here, everybody understands what you're doing? Yeah. Okay. So what is this? If you understand what you're doing, we didn't talk about this concat. So what is this doing? Concat. Any idea what we're doing here? Well, you said you understand, so I want to know how you understand this. So we have 3 vectors, and we have a node which is called concat. What could that be? Put everything in a matrix in a way, okay, but how exactly in a matrix? Yeah, first vector is okay. So you would create a matrix. You can do that. I think we have yeah, but then this will be somehow tricky. Yeah, you could do that, but you will get something else. I mean, concatenation is something else. Yeah. I'm sorry. No, in the back. Sorry, excuse me. Yeah. So yeah, this is a vector exactly. So we need a vector here.
So I think I want to concatenate it in a way that it builds a sentence.
So okay, yeah, you're concatenate. So concatenating is the operation. So you take this first vector, then the second vector after that, and the last vector just after that. So you end up with a vector of size 3 times 50, which is 150. You just put them after each other. This is the easiest operation you can do of 3 vectors, which you want to, if you want to create one vector from each vector, just add them after each other. Easy, works. It also takes into account the position of these words, right? We don't have back of words here because we're saying, oh, we know exactly on the first position what's the word, on the second position what's the word, and on the third position what's the word. It will help us to model, the dependencies, because there's difference. You have to know which words come after each other. So you need to keep that into account. So our initial idea with back of words wasn't that bad, but actually it wouldn't be really helpful because we would be losing the contextual dependence we're modeling. But now we're stacking every vector after each other. So yeah, we are keeping the position of the words after each other. We keep that. So this is a clever design choice. Okay, so this is the concat. Let me just delete this so it's not cluttered. So we have this concatenation function, which gives us a vector here. Okay, beautiful. So now everybody understands what is the first part of that means. So we have a vector which comes to our. Oh, this is just a neural network we just talked about, like in the first part of the lecture, right? So we're having the first projection. So this is the hidden layer. Then we have this nonlinear function. And the output goes to the output layer where we put a softmax over, right? Because we want to predict probability distribution over categories. It's also parameterized by, so it's linear projection, and after comes softmax. Then this is again the loss. Okay, what is Y here? What is the GOAT label? What is going to be the GOAT label here? Yes? The next word, okay, yeah, the next word. So how exactly is it going to be represented? Yes, but well, our network understands only vectors. So what is it going to be? Is it going to be vector? So what is going to be the vector?
So we can either choose the one-hot vector.
Yes.
We want to output.
Yes, one hot vector. So it's gonna be the one hot vector of the next word. Yeah, and then what could be the loss? Okay, so this is interesting. We have softmax and one hot vector. Which loss are we going to use? So we have softmax, which is predicting a probability distribution, and then we have one hot for the gold label. We only know, so you only know 2 losses so far, and one of them will be the loss. Which loss are we going to use here? We're predicting categories. We're not predicting binary, we're predicting over a set of categories. So what is this loss? Okay, you should learn that. What is the loss? Anybody has an idea? It's going to be the categorical cross-entropy loss. Okay, so categorical cross-entropy. So this is important, and you should remember that. Okay, so softmax and one-hot encoding, categorical cross-entropy, binary decision, sigmoid, and just simple binary cross-entropy loss. Okay. So beautiful. Now we have everything to train the model. So we should be able to do so, right? I mean, you can multiply. You can do so. Okay, what you need to implement here is would be the one-hot encoding of words. Okay, this is some little bit of coding. The lookup operation is just matrix by vector multiplication. So we should be able to basically create a new lookup node. Let's put it like that. This would be like a parameter, a matrix, a little bit of coding. Oh, let me just. And so this should be possible. Concatenation. So can we build a function like an? I'm thinking in terms of really like a node. So can we build a concatenation node? Yes. I mean, you just take three arguments, stitch them all together, and call it a day, because we know everything, the partial derivatives and stuff like that. It's super easy. And then the rest is basically already done. So we can really build it. Like we should be able to understand each of the operation in order to build this computational graph and train it. Okay. So why would we do that? What's the advantage of doing this language model? Now before we come to that, like any questions to this? So does it make sense what we are trying to build? We represent everything as a concatenation of word embeddings. We're learning the embeddings, so this is a parameter we're going to learn as well, because we can learn it. It's a matrix, and we can estimate the parameters of the matrix by backpropagation. Absolutely. And the other matrices are too. Yes.
Does this mean the longer our phrases that we're analyzing, the bigger our W get, because it's like 150 times?
Yeah, exactly. Yeah, if we have another word here, edit this and this, then the output would have be like 4 times 50, and then this will also grow.
That's considering a vocabulary that's only 50 words large.
No. Okay, so this is a misconception. No, the 50 is my decision of how the embedding matrix will be, right? So the vocabulary is given, but the 50 is something I decide. It's a parameter of my network, or hyperparameter. So design choice. I'm saying I want to project each word into vocabulary, into a small space of. It could be 2. It won't work as you want. I see. It won't work, but it's fine. Maybe you can try with 2. 50. I mean, so typically you would say a couple of hundreds, maybe 1,000, but less than 50,000. You have a question?
Does this mean I can predict different words?
No. No. You have to make sure. Yeah, that's a good question. I'll come to you next and to you next. You have to make sure that the output of this also matches some dimension, which is going to be, because here this will be of size of the vocabulary. So this also have to be size of the vocabulary. Okay, so you have to make this matrix, the output of this linear projection. You don't care about a hidden layer, it could be anything. But here the output has to be again the size of the vocabulary, because you're predicting over the whole vocabulary the probability distribution. So this has to be like the output of the network. So this has to match your size of the vocabulary. It's a good point. Does that answer your question? Okay, cool. Then you had one and you had one. Yeah.
Just to sum it up. The 50 we chose is like the dimension of the space we project overwards into.
Exactly. So just repeat again, the 50 is a thing we decided. Do you want to project out our words into some lower dimensional space? And we say it's going to be 50 dimensions. Could be 100, could be 300, could be 512, whatever you choose. So this is your design choice. Here, you have to really make sure that you're predicting the same size of the vector, because in the loss, the two vectors have to match, obviously, like on the dimensionality. Okay, you have a question. Okay, any other question? Nice. Okay, so we actually really we went deep, but it's fundamentally there's nothing complicated about it. That's what I'm saying, but you know, you might see differently. But I believe each of these operations should be somehow transparent to some extent. So, okay, so let's build a neural network. I said it already. Well, okay. Input is the k-gram of words. Okay, so that's what we had before. The desired output is probably distribution of their vocabulary. Okay, I said it already. And each input word is associated with the embedding vector from the word embedding dimensionality. So that's what we decided, which we're just talking about. Okay, cool. And the input vector is a concatenation of k words. Yeah, we're concatenating the words after the lookup. Okay, cool. So we already talked about it. Like this is a summary of what we're talking about in the figure. So we discussed that. And now again, it's repeating what we have in the figure in the computational graph. So we built MLP, so multi-layer perceptron with one hidden layer. We can add more actually. So we can really, if we're here, we can stack more hidden layers here. So make a model more deeper. We can do that. Maybe it will learn better. But it will be slower because you need to have like more memory for parameters and more time for backpropagation and the computation. So there's always a trade-off between the size of the model and the time you can spend by computing stuff. So we have MLP, and this is just repeating what we have in there. So the input feature vector to our model is the concatenation of the embeddings. So this is the concatenation of the embeddings here. And then there is a hidden layer. So some projection linear with nonlinearity, which could be ReLU. And the output is going to be softmax over the output layer. So it gives us a probability of word over the whole vocabulary. Okay, so this is again, the output dimension will be size of the vocabulary. This is just summing up what we discussed, like again with the actual formulas. And we already tackled that. So where to get the training examples? Okay, so we already answered it. Training examples are simply k-grams from an unlabeled corpus. So unlabeled means there is no labels like positive sentiment, negative sentiment, or inference, like what was the NLI? Entailment, not entailment, or contradiction and stuff like that. It's basically the next word is the label. So this is easy. This is great because you don't have to do any manual work. You just scrape the internet and have the engrams, and you have as many as you want. So the features are the first k minus one words, and the last word is used as a target label for the classification. So we had it already. And the model is trained using categorical cross-entropy loss. So this is something you should already also know because we're using softmax here. So two vectors, and the loss is categorical cross-entropy. Okay, so this is just summing up what we talked about. Any questions? So anything else you might be wondering about? So advantages and limitations of neural language models. So if we extend the context, if we add more words, we have an increase in parameters, but not that much. So it's a sort of linear increase in parameters. So if we add here, as I said, a new word and, then the embedding matrix stays the same, but we just have to extend a little bit this one matrix and this one bias. Like not 3 times 50, but 4 times 50. Okay, so it will be like dimensionality of 200 instead of 150. But that's pretty much it. So this is another increase. This is good. And of course, the size of the output vocabulary affects the computation time. Okay, why the size of the output vocabulary affects the computation time? Because the output layer requires the matrix vector multiplication with the matrix and the softmax. Okay, because in the softmax, what we are doing, so what is softmax? Okay, who remembers softmax? Yes.
I think it's taking an input and the output is like a one-hot encoding, basically.
There's an operation in softmax. Yeah.
So for
xi.
for the first value, it's the exponential of the first value divided by the sum of all the exponentials.
Ah, okay.
That's not how you calculate it, but that's how you define.
Yes. x1 plus x2 and stuff like that. So, okay, means, but the size, so the E ranges from 1 to size of the vocabulary. So you have to do, if you have 50,000 vocabulary, you have to do 50,000 exponentiations and divisions. 50,000 exponentiations is a lot. It's a costly operation for some reason. And there's so many multiplications as well in the last layer. So the size of the vocabulary is expensive, is empirically expensive. It takes time, like empirically. So that's a bad thing. How to do that is there are some tricks which we are not going to tackle, but I just mentioned in here. So hierarchical softmax or some noise contrasted estimation. Maybe we'll tackle this in the next lecture. But as we build it right now, you need to for every input you need to do 50,000 exponentiations. So it's costly. It's yes.
Is exponentiation costly because we don't need to use E for that. We could use 2 as a base. Then it's just bit shifting.
Okay, bit shifting. Yeah, okay. So I'm not a hardware guy. Maybe you take it offline, but what I remember, the implementation actual frameworks is basically you need to do exponentiation. There's no way around to get a proper probability distribution, you do this exponentiation. You don't do it so naively. You first subtract the maximum of all the values for numerical stability, and we discussed it last time. But overall, you have to do this. I mean, if you want probability softmax and proper probability distribution, you have to do this, like so many exponentiations. So it's much slower than just multiplying a matrix by a matrix or a matrix by a vector. So it's easy, but here you have to really do all these exponentiations. So empirically, it's being shown to be slow. Like this is the bottleneck. If you do this neural language model, this is the bottleneck of computing. So maybe there's better ways around, as we will say later. So we know what are the advantages, how to build a model. Can we use the language models? And I'll finish pretty soon. So now we have a language model. So we have the standard language model, we have the neural language model. Both of them will tell us what's the probability of the next word given the previous word. So we can use it actually for generating text, which means basically spitting out the next word. So let's take we can generate random sentences. This is really awesome. So no input and just random sentences. You start with this start symbol S, and then you ask, what is the first word? What is the most probable word after S? And you can draw the most likely or some sampling. You sample from a distribution, whatever you want to do. And then predict the probability for the next word, given the start symbol and the first word, and so on, so on. How you end this process, typically you also use another special symbol called end of sentence. So either this looks like a HTML tag for a reason, maybe a historical reason, or maybe some EO end of sentence symbol. So there is a symbol, and once you reach it, you call it a day. You generated a sentence. So obviously, if you take just the most probable word at each step, globally it's not optimal. So there's other techniques like beam search. We're not going to tackle them right now, but maybe later in transform models. But generally, you take a word, predict the next word, and just take the most likely one or the second most likely one or one of those randomly. And this is how you generate text by language models, because language model gives you the probability distribution of vocabulary given the previous word. So I want to go, and then you have the vocabulary, B, A, I, M, here's home, and so on. And the language model will maybe tell you that this will have probability 0.05, this will be 0.0001, 0.000000, and so on. So you can choose, okay, yeah, this is the most likely word. Let's take it. Yeah. And continue. What we learned as well, I think we finished. Okay. What we learned as well is a word. We have 2 minutes left, right? Or 3 minutes left. Okay. What we learn as a byproduct, so we train this on the data and we learn all the green parameters of the network. So we learn word representations. One will be here. This will be learned. And also the columns here will be learned. They have different meanings. But what we're mostly interested in is this representation of words here. So the embedding matrix. This is what you're going to use for representing words in the lookup. So this is a byproduct. And basically, it turns out that the language models, the neural language models, actually learn very good word representations. And we will talk about it in the next lecture. What are their properties? How to make it more actually straightforward when we actually only interested in the embeddings here, not predicting the next word, but if you want to learn better word representation here. So we're going to tackle it in the next lecture. But this is a byproduct of that. So word embeddings. Oh, yeah. So these are word embeddings are pre-trained word representation. What do you call it pre-trained? Well, you can just run it on unlabeled data and it will learn the matrix. So unlabeled data means like if you run the neural model or learn the neural model, you will learn this representation of words, which you can then use later on for something else. So you keep this matrix, and the matrix is just saying for a dog, I have a vector of things, and maybe in some space, the dog will be close to a pet, but maybe not the same as cat or bad and good and stuff like that. So this is what we're learning here. This will be useful not only for this language modeling, but for any other purposes, as we will show later. So we can just initialize the embedding matrix E randomly and just learn it during our supervised task. And we can use the pre-trained word embeddings from task for which we have a lot of data, such as self-supervised learning. Okay, so this is actually an interesting concept. I want to highlight it. Self-supervised learning is what we did here. So this language modeling, where we created our data as features and label, well, the label is the next word, and the input is also coming from that. We call it self-supervised because we don't. It's coming from it. The data is coming from itself. The training data are created artificially, basically. We create it on like auxiliary task, predict the next word, but it's coming from the data itself. So we call it sometimes also self-supervised learning. So, and then the desired word embeddings properties, we talked about a little bit. Similar words will have similar embedding vectors. That's what we want, and we'll tackle it in the next lecture more in detail. So recap. So language modeling is an essential part of contemporary NLP. Yes, ChatGPT, all the GPT, it's language modeling made differently, much more complex models. Self-supervised models and unlabeled data, and the next word prediction is a way to train these. And the neural language models learn embeddings of words, and we look into that more into the next lecture. So thanks a lot, and Have a great weekend.